Okay, so as Dr. Vicarino said, I am Erin Brett, and I'm going to be speaking about the influence of metallic biocide concentrations on the time of deactivation of coliforms in river water. So first I'm going to give you an overview of biological sand filters. I'm going to describe how the copper concentration was measured throughout this experiment. We'll review the results of the experiments that were run and explain the first order kinetics analysis that was performed. I will give some recommendations and then conclude and have some questions. So, they just gave a little bit of an overview on what biological sand filters are. As you can see, pour the water through the top. It filters through several layers of media. Fills up the pipes, and then is collected in a container. The two layers that should be highlighted are this metallic biocide layer, which current research suggests that metallic biocides should be placed in the bottom 2 to 3 centimeters of fine sand to have the most coliform removal. This ensures that the copper in solution does not reach the biofilm layer, which is the workhorse of this filter. The most removal happens at this layer, so we don't want the copper to reach the top of the layer, but we also want the copper to work in removing coliform. So before this experiment could be run at all, we had to figure out how we were going to measure copper concentration in our solutions. So I created a standard curve using a hot copper solution, 8 different diluted concentrations. 1 milliliter sample of the solution was placed in each beaker, and then a copper reagent was added. The beaker sat for approximately 30 minutes, and then the absorbance of each was measured using a spectrophotometer. Logger probe was used to have the readings of the absorbance. It was graphed, and as you can see, it was very well fit line. So we used this equation to determine the copper concentration for the rest of the experiments. Okay, so samples were taken from the Okmulgee River. 6 experiments were run at different concentrations. This is an example of the copper concentration at 0.071 milligrams per liter. Time 0, a 5 milliliter sample was filtered, and then for the rest of them, a 20 milliliter sample was filtered, which is why the concentration of coliform was higher in the second floor. But you can see that coliform concentration is decreasing. This is an example of the 0.44 milligram per liter experiment. For the control, we basically did the same ratio of copper to river water, except we replaced the copper with DI water. And as you can see, it remained fairly constant, as it did in the rest of the experiments. And also for this experiment, you can see that within 15 minutes, the coliform concentration was nearly depleted, which, if this is your biofilm layer, it's not a good thing. First order kinetics analysis was run on each of these experiments, and it was found that this system does model first order kinetics, which basically means that using this graph you can determine the first order rate constant, which is, for these trend lines, the slope. rate constants were collected, and as you can see there in the table on the left with the our squared values, it was graphed first order rate constant versus copper concentration. And as you can see, as the copper concentration increased, the first order rate constant increased, which makes sense as copper concentration increases in your sample, the rate at which coliform concentration decreases and increases. Does that make sense? Okay. That's the way. What we recommend is that basically the copper concentration is very low. The lower the copper concentration, the longer it is acceptable to be when in contact with the biofilm layer, which would be those. Yep. Okay, so what this means is that we can now determine where in the filter the copper can be placed, because now we know at what concentrations the copper can be in contact with the biofilm layer for what periods of time, which means that if we can determine the diffusion rate of copper through the filter, we can determine the highest point at which the copper can be in the filter to have maximum removal, but also to allow the biofilm layer to also have its maximum amount of removal. In the future, we would like to test brass and bronze to see if there are any different effects than the copper. Last semester, I did research on brass and bronze, and it was found that over time, bronze actually has a high removal of coliform concentration over time. So next we'd be looking to see, does it also the same? Any questions?
Can you explain a little bit about the first order kinetics and how that works?
Okay, so basically there's zero first and second order kinetics. First order kinetics, if the line is okay, well the way to determine if it's first, second, or zero order is you either plot it based on concentration, the natural log of concentration, or 1 over concentration. That's right, Dr. McKenna? Yeah. So if it is a straight line, that means it is first order, or whichever, respectively. So like the 1.5 milligrams per liter, it's a relatively straight line, which can be seen by the R-squared values. So, and that's just, once you have the graph, you can pull the slopes to have your rate constant, which can tell you how long you're in contact.
So if first order kinetics looks like a y equals mx plus b line, straight line, how would a zero order and a second order line look?
If you're, for this data specifically, it would not be linear. It would be either parabolic or
Second order.
second order.
How would the zero order look?
I do not know. It would not look straight.
Yeah, well, it would just be a flat line. I mean, there's no correlation. This basically says a concentration, doubling your concentration, doubling your removal. Yeah? Would you go back to your picture?